Well, we came back with the last speaker of the session, Daniel Labardini-Fragoso from UNAM, Mexico. And he's going to speak in generalized cluster algebras, Caldero-Chapoton algebras, or gentle algebras.
Thank you. Yeah, thank you, Sonia. Let me turn on my camera. Yeah, so I guess you can see me now, right? Yeah.
Yes.
So, yeah. So thanks to the organizers for the invitation to speak here. I wish I could be there. So I'm going to talk to you about some past work that I did with Diego Velasco and some work in progress that I'm doing with Langmo about some Caldero-Chapoton algebra approach to certain generalized cluster algebras. So let me start by reminding a little bit about Chekhov-Shapiro's generalized cluster algebras. So I'm going to work with unpunctured surfaces with orbifold points of order 3. Yeah, and so, such a surface is just a triple consisting of a surface sigma, which I'm going to assume to have a non-empty boundary. Okay? A finite set of the boundary, the marked points, and I'm going to assume that each boundary component contributes with at least 1 point, and then a finite subset of the interior of the surface, which are the orbifold points, which are going to be those orbifold points of order 3. So here you can see some examples, right? So the hexagon, and here I put one orbifold point, and here the torus with one boundary component, one marked point on it, and one orbifold point. Yeah, and then let me just tell you a little bit that of course the general picture is a lot broader, let's say, because in general one allows, for instance, the boundary to maybe have, the surface to maybe have empty boundary, and also one may allow the marked points, some of them to lie on the interior of the surface, and the orbifold points, they don't all have to be of order 3 in the general picture, right? So this is kind of a very specific situation, unpunctured surfaces with orbifold points of order 3. So it's kind of a lot of restrictions. Okay, and then as you may expect, I'm going to work with arcs and triangulations of the surface. An arc, as you may expect, is a curve that is not homotopically trivial and does not cross itself, right? So, and what I ask of it is that it connects points of M. So no arc goes to M. So, for instance, I can have like this would be an arc, for instance. This would be another arc. And then, for instance, these two arcs would be not equivalent on their isotopy or on their homotopy, because the homotopy would have to pass through the orbifold point. This would be another example of an arc, right? And then a triangulation is a maximal collection of arcs that do not cross each other, right? Up to isotopy, right? So, so here you can see some triangulations, and here you can also see the notion of flip, right? For instance, consider these two triangulations. The only difference between them is this arc, the arc surrounding the orbifold point. So these two are related by a flip. And similarly, for instance, this one and this one, the only difference between them is these arcs, right? So they are also related by a flip, and similarly, this one and this one are related by this flip, right? So, so in this setting, we again have the notion of flip. And what Chekhov and Shapiro do is they associate some cluster-like algebra to such objects, right? So that they call generalized cluster algebras. Yeah, yeah, that they call generalized cluster algebras, and that as you can see, somehow the underlying combinatorics is kind of similar or reminiscent to the combinatorics of a cluster algebra. And so to associate such a kind of cluster-like algebra or generalized cluster algebra, what they do is to each triangulation, they associate some skew symmetrizable matrix, right? So here I'm not going to tell you the exact rule for time reasons, but one way to read this skew symmetrizable matrix from the triangulation is by first somehow like placing some valued quiver here, and then from the valued quiver, one sort of just reads off the matrix, right? So that's kind of at least that's the way I compute these matrices when I sit down to do examples. So here you can see these two triangulations, which, as I said, are related by the flip of this arc, and one you can just check that the corresponding matrices are related by a mutation, by just a mutation of matrices as in Fomin and Celebinsky, right? So here you can see another example of these other two triangulations, which are again related by a flip, right? And the two associated matrices, and again you can check that these two matrices are again related by a Fomin-Celebinsky matrix mutation. And here comes an observation, like kind of a crucial observation, which is that not only are these matrices skew symmetrizable, and I think about the skew symmetrizer as skew symmetrizing it on the left, but also there exists a tuple of positive integers such that the column J is divisible by the corresponding integer. Like for instance here 1, 1, 2, 1, 1, and the same tuple works here, and then here you can see is 1, 2, 2. Right. So this is kind of a crucial observation in order to define kind of a delta variant of mutation, right? So so with this tuple, right? If you give me a seed, right? Let's say this is an n by n matrix, and then this is just x1 to xn, right? And then they define the mutation, kind of this delta mutation of the seed, to be this other seed where at the level of matrices you just it's just the Fomin-Celebinsky matrix mutation, but at the level of seeds, what you do is now replacing xk, instead of by a binomial, you replace it by this kind of longer polynomial. And yeah, so this is here you can see it's a reciprocal polynomial evaluated in the two factors, in the two terms where you evaluate the binomial in the usual cluster algebra, right? So and of course this is not the most general setting in which this is not the most general definition of mutation of seeds given by Chekhov-Shapiro. It's kind of, I just wrote down something, the one that is going to serve my purposes. So let me give you an example. So here I have this matrix. Here you can see it's kind of 1, 2, 1 does the job, and my generalized cluster. And the first mutation, well, matrix mutation, you know how to do. And here here somehow it turns out that this is just kind of how it would look if we were just in a usual cluster algebra for the third delta mutation as well. But for this one, you see here this term, this new cluster variable then becomes this trinomial divided by x2, right? So sorry. You get something different, right? So the kind of what I want to stress here is that sometimes it may look like an ordinary mutation in a cluster algebra, and sometimes not, right? It's not that it always looks different. It's just that it really depends on the integer you have there. And then of course, just like Fomin and Selevinsky, Chekhov-Shapiro started mutating with a fixed choice of delta, right? And what they generate, they call the generalized cluster algebra. Right? Something they prove is that these generalized cluster algebras have the Laurent phenomenon, and somehow one natural source of generalized cluster algebras comes from Teichmüller theory, right? So the point is that surfaces with orbifold points, they arise naturally when one considers Fuchsian groups that have elliptic elements, right? So Fuchsian groups, that is discrete subgroups of PSL2R, that are not torsion-free. And when one considers the quotient of the hyperbolic plane by the action of such a group, then one obtains a surface with orbifold points. So they do arise naturally in geometry. And it turns out that the decorated Teichmüller space of such a surface is a generalized cluster algebra, right? So it's kind of similar to what happens in the unpunctured case by the works of Penner, Fock and Goncharov, and Fomin, Shapiro, Thurston, and Fomin, Thurston. So that picture is kind of, there's a completely parallel picture here, right? Where the cluster variables are parameterized by arcs on the surface, and the clusters are parameterized by the triangulations, and the flip of triangulations corresponds to mutations of clusters, but now mutations in this sense. Okay, and then of course, kind of there is then a natural problem, which is can one realize such things, such generalized cluster algebras, or at least these ones, at least the ones coming from surfaces with orbifold points, as Caldero-Chapoton algebras of some associative algebra. Like, can one define some Caldero-Chapoton map in order to hit those cluster variables, right? For instance, and this is something that Diego, Velasco, and I did some years ago. And so we did it for the polygon with one orbifold point of order 3, right? So this one is because it's one orbifold point of order 3. So for each triangulation, we considered certain algebra that can be described as the Jacobian algebra of this quiver with potential. The quiver is kind of defined as you can imagine, right? So the arcs of the triangulation are the vertices of the quiver, and then one draws arrows clockwise within each triangle, and then one takes the obvious potential, right? So let me show you these examples. So here, of course, I consider this arc as being adjacent to itself in the triangulation. I actually consider it to be a triangle, so somehow like sort of degenerate, but still a triangle. And this is why I draw this arrow in the clockwise fashion, right? And then the rest is what we are all used to do. And here the potential is alpha beta gamma plus epsilon cube, and similarly here, right? So here you can see this this arrow, then is a loop of the quiver. Here you have another example, and which I drew kind of just so that you see that some familiar algebras, right? Some algebras that you have seen in the work of in the works of Geiss, Leclerc, Schroer arise here. And it turns out that the Jacobian algebra is finite dimensional and gentle, right? If let's say that I work, let's say over the complex numbers or a field of characteristic different from 3, right? And then the point is that this 3, when I take cyclic derivative, somehow the cyclic derivative with respect to epsilon becomes 3 epsilon square, and you see in, let's say in the complex numbers, you really get epsilon square. So somehow this 3, there is no conflict, right? So this 3 becomes, you see, becomes a 2 in the Jacobian algebra. And what we proved in a slightly different language is that there are bijections between the arcs in the polygon and the tau rigid in the composable pairs of the algebra. The representations can be read off quite explicitly from this one, right? I mean, we're kind of in not very complicated gentle algebras, and moreover, when you take 2 triangulations related by a flip, and you consider, let's say, by the flip of an arc K, and then you consider, as usual, the product of the Caldero-Chapoton map of the new arc that replaces K times the Caldero-Chapoton map of the old one. This gives you precisely the exchange polynomial of Chekhov and Shapiro. And well, I will show you an example in a second. And so the Caldero-Chapoton algebra of this gentle algebra, which is just the kind of the ring generated by the Caldero-Chapoton maps of the representations, is isomorphic to the generalized cluster algebra of Chekhov-Shapiro. And the set proposed by Geiss, Leclerc, Schroer as a basis, so the so-called generic basis, is indeed a basis. So let me show you some examples. Well, so for instance, here I'm working with this. The underlying algebra is this one that we have seen in the works of Geiss, Leclerc, Schroer, right? So the pink triangulation is the kind of the originally fixed triangulation. And let's say that we take this pending arc and this other pending arc. And so here you can see the associated representations. Okay, and then let's consider 2 triangulations. You see one triangulation containing this one, another triangulation containing this one. So you can see them here. Yeah, so I really have to learn how to move around. Okay, so so you see here, this one is here, and this one is here, right? And the 2 triangulations I picked are related precisely by that flip. And what one computes is that this product of Caldero-Chapoton functions of you see the kind of the old one times the new one is precisely this, right? Which is Chekhov-Shapiro polynomial evaluated in this arc and this arc, right? So it is this one square plus the product of these 2 plus this one square. Okay, and this for instance, this you can just compute directly, at least in this example. And of course, there is still a question which we didn't solve back then. which is, okay, now what if you change your initial triangulation, right? So what's the relation between the two algebras, right? Like for instance, if we were speaking about surfaces without orbifold points, then we would know that at least the underlying quivers with potentials are related by a Dirksen-Weyman-Celebinsky mutation, for instance, right? So far here we don't know it, or at least at that point we didn't quite know it. And this brings me to the next section, which is what I'm currently doing with Lang-Mo, which is try to generalize what I did with Diego to now arbitrary surfaces with orbifold points of order 3, but arbitrary unpunctured surfaces, right? So that I still I can still guarantee that my algebras are gentle. So all of this is in progress. So hopefully soon we will have something on the archive. So now take any unpunctured surface with orbifold points of order 3. And we triangulate it as we did before with the polygon, and play the same game, right? So now, since now you may have many orbifold points of order 3, now maybe you have many of these arcs, or of these kind of pending arcs. So you really take this sum, right? Okay, but in any case, it's somehow the obvious degree 3 potential on the quiver, and here you have some examples. So here the surface is the diagon, and we have 2 orbifold points, and for that triangulation, you can see the quiver here, and this is the potential. And when I flip this arc, I get this other triangulation, and you see, and this potential. Okay, again, the Jacobian algebra is finite dimensional gentle, and we have a result similar to the one Diego and I established for the polygon. Namely, there is a bijection between the set of arcs on the surface and the tau rigid in decomposable pairs. And when you have 2 triangulations related by a flip, then the associated Caldero-Chapoton functions satisfy the multiplication formula dictated by the delta mutation, right? So by Chekhov-Shapiro mutation. Yeah, so here just an observation, right? So that as you know, that the arcs in the original triangulation, we make them correspond to the shifted projectives, right? So kind of to the projective kind of in the decoration, and these land in the initial cluster variables. All right, and we have somehow also some sort of answer to the question of what is the relation between the 2 algebras. And what it turns out is that if we have 2 triangulations related by a flip, then the associated quivers with potential are related by some version of mutations of quivers with loops with potential that generalizes Dirksen-Weyman-Celebinsky's mutation, right? But here I have to say that somehow okay, this is a generalization of Dirksen-Weyman-Celebinsky's mutation, but what it turns out is that in their setting, Dirksen-Weyman and Celebinsky, they were able to prove that for any quiver there is a non-degenerate potential, right? Let's say if you work over the complex numbers, and that is what fails in our version. So for our version, yeah, okay, yes, it's more general, but you cannot prove that every quiver admits a non-degenerate potential. It turns out that if you work in this specific setting of this triangulations of these surfaces, then you do have non-degeneracy because of this. So in a way, it's kind of it's a generalization, but it's not like really far-reaching generalization. It's just kind of a good enough generalization that it works for triangulations of this type of surfaces with orbifold points of order 3. But at least this allows us to have generalized reflection functors, and to mutate at sources at vertices that are not necessarily sinks or sources, right? So in a way, at least in this setting, we are able to to mutate at some vertices that, let's say, Geis-Leclerc-Schröer in their much wider setting cannot mutate, so let's say, right? Some other kind of defect of this mutation is that we can define these generalized reflection functors, but what we cannot do is define mutations of representations, as in the work of Derksen, Wiman, Celebinsky. And this is because since our algebras now are, you see, of this, when you have these loops, you really have the algebra. You really have the algebra K epsilon divided by epsilon square. And then submodules and factor modules of free modules over this algebra, we know they are not necessarily free. So you cannot choose, you cannot always choose a section or a retraction as in the work of Derksen, Wiman, Celebinsky. So we have these functors, but we do not have a mutation of representations. So kind of some things you win, some things you lose, right? So, and let me finish with some current work with Lang. So one of the things we expect and we would like is that, as in my work with Geis and Schröer, that there be a bijection between the laminations of the surface with orbifold points of order 3 and the tau-reduced components of this gentle algebra, right? So here, let me recall that now Geis, Schröer, and I are calling tau-reduced components what originally was introduced as as strongly reduced irreducible components by Geis, Leclerc, Schröer. Another question is whether the set proposed by Geis, Leclerc, Schröer, the so-called generic basis, is indeed a basis of the Caldero-Chapoton algebra. Of course, besides this, there's a question of whether the Caldero-Chapoton algebra is equal to the generalized cluster algebra. By now, we only know that the generalized cluster algebra is contained in the Caldero-Chapoton algebra and is contained in the upper generalized cluster algebra. Is Geis-Leclerc-Schröer's so-called generic basis invariant under mutations, right? How you see we have the gentle algebras, the indecompulsables are given by strings are bands. So how do the Caldero-Chapoton maps of these representations compare to the expansions in terms of kind of some generalization of snake graphs given by Banayan and Kelly? And you see, how does the Caldero-Chapoton map compare with the Caldero-Chapoton map of the locally free quiver Grassmannians, right? So kind of, does the Caldero-Chapoton with locally free quiver Grassmannians, so where you only take submodules that are locally free, do they give you the cluster variables for the cluster algebra with orbifold points of order 2, right? And here there is no mistake. Here it's not order 3. This would be order 2, right? So something similar to what guys like Leclerc have shown, let's say, in some linking cases, right? And finally, last but not least, we think we can complete Bruce-Smith-Treffinger's tau tilting stability complex to a scattering diagram. And for this, let me just show you what we mean. So this would be when the quiver is just this one. And here, this would be the scattering diagram. This appeared in Lang's PhD thesis. So somehow, what we are saying is that this is the stability scattering diagram of this quiver with epsilon square equals 0. And then hence completing somehow the picture introduced by Bruce, Smith, and Treffinger. And I think that's it. Thank you. Thanks a lot.
Okay. We thank Daniel for the talk. Well, are there any questions, suggestions, comments? Any questions in the chat?
I have a question.
Yeah.
So if in the case where you have orbifold points of degree 2, or order 2, I should say, this is Velasco-Shapiro to Markin, if I have the right list of things, and they were able to understand these through sort of an unfolding, or they unfold them and then they find a surface where you can fold it to get the surface with orbifold points. Is there a similar kind of thing here? I mean, I think I can see it in the case of the polygon with one order 3 orbifold point. You could take a centrally symmetric triangulation with an order 3 rotation. Is there some sense in which you could understand some of these other cases by unfolding?
This I don't quite know, but in the case of the polygon, you are completely right. I mean, that's somehow actually the strategy we took, Diego and I. We took this branch degree 3 cover, and you read things upstairs, and then you have a push down functor, and then we use the results of we used kind of very essentially some results of Paquet-Schiffler in order to establish this. Where is it? In order to establish this formula. So in that case, yes, it can be applied. Sorry, this formula. Sorry, yeah. And in this case, yes, it can be applied, and at least in the work with Diego, it kind of we really relied very essentially on that. In the other case, kind of in this more general case, we are trying to avoid these covers, these kind of degree 3 covers. I mean, we're trying to do it kind of just kind of as direct as we can.
Thank you.
Okay. More question? Here is a question. In addition
more
to
a comment, just trying to supplement what Daniel was saying.
Okay. In addition to what Daniel said, Esther and Elizabeth looked at this as well. One issue is that even you have 2 orbifold points, you get an infinite cover that looks like an MC Esther painting, hyperbolic disk. Okay. More questions or comments?
Yeah, I have one question, Daniel. Thank you very much for the talk. It was really interesting. And are your algebras always finite dimensional?
Yes.
Okay.
Yeah, and I think this, yeah, they are finite dimensional, and I think, and this is not hard to prove. Somehow the point is somehow let's say kind of the intuition is that if you have a marked point, since you have boundary, you cannot circle around it. So it kind of the path becomes zero very quickly in a way.
Right.
Yeah.
Okay. Thank you.
Okay.
So coming on this, so each time you have one of these three, one of these orbifold points of degree 3, this always implies that you have one of these triangles, which is of one arc, corresponding with one arc.
Right. Yes. Yeah. And somehow the kind of geometrically the picture you should have in mind is somehow that take let's say an equilateral triangle, and then apply the rotation by
right.
and then so somehow that's what happens. Yeah.
Right. I see. Yeah. Thank you very much.
Okay. Here in the chat, Matt Fresland have a question in the room. Matt, you have a question? No?
Yeah, I cannot hear.
No, I cannot see. Matt Fresland, you have a question?
Yeah, they have some sound problem.
Yeah, well, okay. Some technical problem. Okay.
Yeah. So in the meantime, maybe let me read Greg's question.
Mm-hmm.
So yeah. So is there any hope of extending some of these results to orbifolds with a point of order greater than 3? I don't quite know. I mean, somehow you see, there is something I have really struggled to understand, which is, well, many things, right? But the one in particular, which is the following. So if you want to deal with orbifold points of order, let's say p, here you have to write cosine of pi divided by p, if I remember correctly. And so you see, the thing is, this can be like even an irrational number. So how could you get it from? You see, how can you get it? Like here, you see, you would need to obtain it here, which means that these ones, which so far always have integer coefficients, somehow they should give you some irrational number sometimes. Yeah, and Misha Shapiro at some point told me that maybe it's possible to rescale, to do some rescalings in order to change this coefficient here. But I mean, but to be honest, I don't understand how to do that rescaling. So right now I would say I don't know how to obtain orbifold points of higher degree. Yeah, thank you for the question.
Okay, now is the Matthew's question in the chat. Do you use gentlest in the mutation result or just the rejection?
Well, I mean, we do use that. We have a lot of control on the fact on how that you can see the indecomposables by means of curves on the surface. So in a way, we are using gentleness kind of in a somehow I would say almost essential way, I would say.
Okay, there is another question. I have great question also in mind. I work about Pasquale Velasco and is related to work of Fraser on generalized cluster structure for the cyclic symmetry locus.
Yeah,
of the
I see.
Riemannian.
Yeah, I think somehow what one should understand is this suggestion by Misha Shapiro of how you rescale in order to be able to change this coefficient cosine of pi over p to some other number. Yeah, but I honestly don't understand what he means by this rescaling.
Another question.
I'll go ahead and say it. So just a different thought about Greg's question. There is something fundamentally different about the numbers 2 and 3 in the surfaces model, in that they're the orders of symmetries of sort of somehow your fundamental objects, if those are arcs and triangles. So if you wanted to get order 4, again, this is very, very much tied to the idea that you want to be doing unfolding. But if you want to come from the surfaces model and get order 4, you'd have to do something like 4 arcs at a point, which maybe is just going to look fundamentally different.
Right. Yeah. For instance, if you take one of these triangulations that I talked about today, and you take the degree 3 branched cover, what you actually obtain a triangulation, right? Yeah. But if you take if you, let's say, move to orbifold point of order 4, and you take the degree 4 cover, what you have is kind of a square in the center. So yeah, I don't know if it's related, if the problems arise from that, but somehow, yeah, you stop getting triangulation substairs. Yeah.
Okay, thank you. Are more questions or comments? Well, if not, we thank Daniel again for the very nice talk,
No,
and all
thank
the
you.
speakers of the session.